Hi guys, welcome back to my channel. In today's video we'll learn what partitions and filtrations are, alright? So partition is a pretty simple thing. It's just a partition of a set omega. We learned in the last lecture what of this big omega is, right? It's a set of all the possible values that we will observe in a time horizon, right? So a partition of a set omega is a collection of non-overlapping subsets of omega whose union covers the whole space, alright? So in the partition definition, this non-overlapping is a little important. It's pretty important, okay? If it's not non-overlapping, then it won't be called a partition. So mathematically, I can write this definition in the following ways, okay? Suppose I take a collection of subsets of sigma. Let's call those subsets A of n, where n equals 1 to k is some arbitrary number. If I take these subsets, then the subsets will be a partition of omega if the intersection of all of these sets is phi, which means that the pairwise is disjoint. Okay, this is what I wrote here, non-overlapping. Okay, that's what it means. That's pairwise disjoint, and the union of all of these subsets forms the original set big omega. All right. So this is what it means, that whose union covers the whole space. Okay. So that's just what it is. That's what a partition is. And the smallest sigma field forms a partition. So the smallest sigma field, as we all learned in the previous video, that the smallest sigma field of a set omega is phi and omega, right? And this itself forms a partition. So this is the smallest partition possible. Now what I'm going to do, so basically partition is like if I have 1, comma 2, comma 3, comma 4, comma 5, comma 6 in a set, and this is big omega. So the partition would be something like 1, comma 2 and 3, comma 4, comma 5, comma 6. So this can be called a partition. So this, it does not break any of the rules of the partition that we learned over here. So that's all it is. That's what a partition is. So now let's see what a filtration is. Okay, so now let's see what a filtration is. A filtration is a little important. Okay, so we want to consider the elements in a sigma field as events, right? Because then we can assign probabilities to them or some number to them. With these events, we can also have information like the event that has occurred or the event that will occur, or at what time instance will the event occur. So as we all know that the set big omega is basically the set of all possible outcomes in our entire time frame of observation for some event E, right? Let's call some event E. This will have all the possible values for this event in the entire time frame of observation. And the sigma field represents the events that are observed and can be recorded when the experiments are performed, right? So the sigma field basically, as we learned in the last video, it represents the events that are observed, okay? It will be some subset of the big set omega, of the set big omega, and they're basically events that are observed, right? And can be recorded when the experiments are performed. So suppose, let's just take an example that we toss 3 coins. Let's say that we have 3 coins, right? And we toss all of them. So now our entire entire field of observation this big omega will be h h h h h t, right? All the way. If we take all the combinations, we'll have t t t, right? But at each time period, we can only know what the first what the first coin gave us the output as, right? So then our first filtration F1 would be H H H H H T H T H H T T. Similarly, this will be divided into two parts because at time t1 we only know what the first coin gave us the output. So T H H T H T T T H and T T T, right? This is at time t1. If we go to time t2, when you toss the second coin, then we would know, then we can further divide this into four parts: H, 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 T, right? Depending upon what the second coin gave us. Then we can have H, T, H and H, T, T, right? Similarly, we can have T, H, H, T, H, T, and then T, T, H and T, 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 right? This is the filtration F2. And then at time t3 we can have filtration F3, which will be all the values separately, because at this time instant we know exactly what output we got. So we can have H, 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 then H, H, T, then H, T, H, this all the way to T, 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 right? So here in the first filtration we'll only have two outputs for the event. In the second filtration we'll have four outputs for the event, four possible outputs. In the third filtration, when we have all the information related to our event, we'll have eight possible outputs, which will be the entire sigma, which will be the entire set big omega, alright? And here we can also observe that each filtration, if filtrations progress in a time like T1, T2, T3 in a linear order, then every single time F1 will be a subset of F2 will be a subset of F3. If the filtrations progress in a linear time T1, T2, T3 all the way to Tn. Alright, so that's what filtrations are. They're just basically events that are observed and can be recorded when the experiments are performed. Okay, so with this we are done with partitions, filtrations. In the next video we'll start measurable spaces, so I'll see you guys there.